Yeah, thank you for the nice introductions here. And yeah, I'm quite happy to be part of this nice meetup for some months now, and yeah, to have some friends to look into this book. What is Rust Atomics and Locks by Mara Bos. So we will today dig into chapter 4 and 5, and this will be very implementation heavy. So I have a short agenda here. So we will build the spin lock, and when I looked over it, I realized, okay, this minimal implementation, it really reminds me on how C++ synchronization types are, because they are not linked to the data or chained to the data in any way. And we will then have the types that is changed to the data and a short quiz, and in the end, a safe implementation of a spin lock. And after that, we will build our own channels. And yeah, there are a lot of implementations, 7 by number. And yeah, I hope afterwards we will have some time for discussion and also hearing about your experience when you were reading the chapters. So, but to start, what is the motivation of a spin lock? So for use cases where you really need low latency, there a spin lock is a good way, because you are in a busy loop trying to look, and by that go into the performance trade-off to waste a bit of the CPU power, but therefore have low latency, instead of using like methods like sleep, who can end up in a really high latency because you are out of control, the OS takes over control. Okay, so this minimal spin lock implementation, we see on the right side here, it consists of one atomic pool, and we heard about it on the other chapter 2. So there are some methods on it, we will see them. And we also need the content of chapter 3, which were both given by Anup in the last weeks, about memory ordering for acquiring and releasing the lock. So in the implementation itself, we start with a simple construction with a not locked state. And then we have the lock function, which swaps a true value into the atomic. And if the state before that was false, this previous state is returned, we just skip the loop and would end the method at this point. And if it's not true previously, we give a hint out that we are in a spin loop, and this allows further optimization to happen. So it's quite, there are a lot of architecture details. So like in chapter 7, we will hear more about this, but what is also interesting, there's another method, it's called thread yield, that also does something similar. I also added an alternative way with a compare exchange method. I personally like this a bit more, especially as soon as you don't use booleans, but integers, for example, you can really compare for a current state, which should be false in our case, and our new state should be true. And we get back a result, and when there's an error in the result, we know, okay, our previous state, it was not what we expected, and so we can loop. And in the unlock method, we just store the false value in the atomic boolean. And yeah, here, these two memory orderings, they are quite important. to ensure that we have like one, that we're quite sure that we have like a synchronization points also between threads. So, all right. So on the, what I already said is like there's no data linked yet, and that is what we want to do next. So we will implement an unsafe spin lock and get a reference, a mutable reference to some type T. And in the implementation, we add a value that is stored inside an unsafe cell. And this unsafe cell, it allows interior mutability, which is needed because we cannot have mutable objects on several threads. So it allows to get mutability at runtime. And for me personally, I really liked this quote here, where Mara was talking about calling this exclusive and shared references instead of mutable and immutable. Yeah. Let's check. We have a constructor here. That's just initialization, but what is quite important are the traits below here, because we want our spin lock to be synced. That means that it can be used on 2 threads at the same time, and therefore the containing type T must be sent. What means it can be used on different threads, yeah, on different times. Okay. We also have now another lock and unlock function. The signature changes, we return a mutable reference here. And yeah, we remain with the swap variant to acquire the lock, and we dereference the pointer that we can access on the unsafe cell, and by that get a mutable reference to this. And dereferencing a pointer is unsafe because we really need to assure that we have unique access here. And what was also in this implementation of the unsafe spin lock, we cut a lot of burden to the user with this documentation where we say, okay, you have to ensure that this mute reference is gone. From the code, the method does not change, but I had a bit of fun to just let things explode. So 2 bad things. So we're using our implementation here just to create a spin lock over a string called hello world. And then we use this spin lock to create 2 references that are mutable and do the worst thing, like just opening up a scope for threads and spawn a thread that pushes 10 times 2 into the string over ref1, and the other one it pushes 10 times bar into the string, and in between we have some sleeps. And in the end, we look what is the output. And so I did some small quiz there, and it's a multiple choice quiz. So I already see here there's some chat messages. Just put it in the chat what you think can happen. So is it a yes for a heap corruption? You can go with B, if you think, okay, there will just be an unclear order of foo and bar. We could also go with C, when you think we will ending up in an endless loop. And D would be like more undefined behavior. And yeah, to go to the results here, it's literally it's really complicated, because I wasn't like expecting to find a sign here, a equal sign, and this heap corruption. I wasn't also expecting this when I was running that. I saw also an endless loop, but it was hard to reproduce. And yeah, that's the thing when you do this stuff like on the heap and playing around with the memory from different locations. It's really a dice roll. Undefined behavior maybe not happen too often, but it can happen. Okay. So maybe some words on unsafe. For when I read about that, I was thinking like, okay, that's really the strong argument for Rust. We have like C++ like powers, but really great communication about where we have to be really aware of what the code does. And what I would recommend is, if you're interested in this stuff, just check out the Rust book, chapter 19.1. It shows which kind of unsafe operation exists in Rust. Okay, so was there a question?
No questions.
Oh, all right. I thought I heard something. Okay. Yeah, we want to come up with a spin lock, and there's also the second thing that I observed, like when you really want to enter with safe APIs, you have to use the type system a lot. And we will use lifetimes and also the traits deref, mood, and drop. And yeah, so we have actually the same structure, so the same variables in the structure and the same constructor. But what is new is this lockout type. And here we need the reference as a lifetime to tell the borrow checker where he gets the information on how long the references are allowed to live, so that we get meaningful error messages if we do something wrong. And yeah, so the log message changes a bit. So we now generate this new helper type, and yeah, this part remains the same, and we just generate the object with a reference to self and return this object. But the magic happens in the traits. So what we have here is, like, when we have this guard as a variable, we can just access the underlying type as a deref coercion. And that's what's actually happening here. So we again use an unsafe block to dereference the pointer in the unsafe cell and get either a normal reference or a mutable reference to the underlying data. And yeah, we also need the drop trait, which is responsible to then release the lock again. So drop is called when the variable goes out of scope, or if you call it by yourself. And in C++, it's known under the Rye idiom, if you want to check this out. And we also did a implementation test here. We spawned a spin lock with a vector and 2 threads that push either the one into it or two times the two. So this goes out of scope somewhere here. And by this lock operation, we ensure an ordering. So either you see a 1 to 2 because the first thread is executing first, or the other way around, 2 to 1. Okay. Yeah, that is what I said. We can also call drop manually instead of waiting off leaving the scope, and then we get meaningful error messages that we cannot use this guard G anymore because the borrow checking over the lifetimes, it's not ensured anymore. During this chapter, I ended up with some references. So here are here's the unsafe chapter in the Rust book. Here's a nice Stack Overflow question where the send and the sync trait are explained in more detail. I also ended up to find a very nice question where was an answer that digged into how you could implement a low latency ticket system with spin locks. And I think there's also an older video of the group in YouTube. And that's why this chapter is quite short. And maybe to shortly summarize it, we're using busy loops here. It may reduce the latency. Always benchmarks this. These 2 types, atomic bool and unsafe cell, are the ones we used for the implementations. This happens before relationships. I think it didn't highlighted it too much, but we had an entire chapter about it. Like the acquire and the release are responsible to ensure that before you read or store something into this atomic Boolean, that everything is done before that. That is, there's no open operation. That from this point on, all threads will see the same, even when there are many threads. Well, I have a strong opinion on unsafe, like, and especially putting burden to the collar. Don't do this. It feels for me just going back to the 90s with some libraries there. And what was the main learning, I think, is using this trait and the type lock guard to have a really nice safe API. Okay, short drink.
Can I say that there was one point that you missed out with chapter 4 before you go on chapter 5, and that's the one of the reasons for the one of the reasons for the guard was to control lifetimes. So the idea was to make sure that when you get access to the interior value, its lifetime only lasts until the unlock call. And the only way to do that was to have a separate thing, a guard. And the book, the chapter goes into a really, that's a paragraph or 2 on lifetimes. And that's a really good read if you want to understand lifetimes a little bit more and learn how to manipulate them. That's all.
I think there's a lot you can learn about lifetimes, but in the book it was quite short, but a good summary. Okay. All right.
Yes, you can learn everything about lifetimes reading that chapter, but specifically for this, it was interesting to read.
Yeah, that is a read that is missing, but I'm happy when we add more to the list later in the discussion. All right. So channels are used to pass data between threads. So it's for communication. And well, Mara, she really highlights how usage dependent or use case dependent it is. So maybe you optimize it for throughput or latency, and you have like this, single sender, single receiver, or multi-sender, multiple receiver, single sender, multiple receiver. So there are a lot of options, blocking, non-blocking. And we also will have a look at a lot of them. I try to get an overview. And yeah, we will start here with also, implementations that use primitives and stud. So, and then start with a working example from the with an unsafe channel as to build on. So here we use in the mutex channel we use mutex that wraps vecdq. So this was chosen here because in comparison to a vector, we can also delete and push something on the front quite fast. And we have a condition variable to inform another thread that there's something ready to be received. So the constructor is quite easy. We use the new operator to get our variables initialized. And then here in the send message, we send a message of type T. Therefore, we acquire a lock over the mutex type that may fail. So we unwrap it to get the vecdq and push back a message. And when we're done with it, we use the condition variable to notify other threads that may be waiting about the that there's a message. And that's very interesting in the receive. We get a guard B, and we get this by locking the queue again. So the mutex returns a guard object, and we just hold the guard for some time to check once if there's a message, and if there's a message, we return. And otherwise, we use the condition variable and give it the guard, such that in its wait method, the guard gets unlocked. And as soon as wait returns, that means this thread got notified. We generate a new guard and reiterate the loop. So there were many drawbacks given in the book. So first of all, every send and receive, it locks one mutex, and depending on how many threads you have, you may that is maybe not what you want. And especially if you think about reallocation, that's when the memory of the queue is not enough anymore and it has to grow. It blocks every thread for a long time. And what could also happen if you have a really slow receive, you can end up to grow out of bounds and fill up your main memory because the queue is just growing infinity. And so what we want to do here, we use a one-shot channel. So it's just sending one message, and we use nearly the same types as for the spin lock, but we also use maybe uninit, which is the unsafe option variant, so to say. So we have uninit memory for the type T. And we have an atomic boolean that indicates if the receiving side is ready. And we also need to implement the traits. And yeah, here in the constructor, we use an uninit representation of this type. So it may be random memory. And yeah, there's, for example, we implement the send message, and send, the message itself is unsafe. So this time we tell our caller or user that we have an unsafe message here, and that he has to watch out, or she. And what we do is we access the reference in the unsafe cell, and then use the write function of maybe uninit. And well, what could happen here is maybe when several threads would try to access this message, you have a data race, or if you do it multiple times, you would leak memory because it won't drop the previous type. So that is only true for types that allocate memory on the heap, like string or vector. But yeah, important to know. And if you're ready with the end, we store true in the flag and release it to other threads. Okay. We also have a receive message, and on top of that is ready message. So this ready method is quite important for the user of the channel, because otherwise the user cannot protect against undefined behavior, because when we misuse this, we this receive method, which is unsafe, it must really be called when isReady returns true. Otherwise, this assume init. This assumption doesn't hold, and we end up with undefined behavior. And what I also find quite interesting is that this thing, it only it generates a bitwise copy. So if you get like something out there, when you move something out, you have a drop operation, so the drop will happen, but not if you so okay, that is another topic. But what I want to say is, like, if you would use it for other use cases, as you may have to double check if you not actually want a deep copy or a duplicate. Okay, so now we start to go from safe to from non-safe to safe. We are runtime checks, and we use panic, so no undefined behavior. And yeah, so we start by improving the receive method. So it's still unsafe. So the table is a bit badly labeled. And what we do now is, instead of having undefined behavior, we check if ready is false. If we acquire a false in this thread, we just panic and say, okay, there's no message available. And we also need to update send. And there we'll want to panic if multiple messages are sent. I think I didn't write it yet. So in use is is a new flag that we will use in between. And that's because we have like two states in the send message. First of all, we swap true into in use. And if it is already in use, we know, okay, we try to send a second message. And yeah, the rest is as before. We write the message into our wrap type and store true in ready and release it to other threads. And now we are ready to also improve receive to make this at least a safe version. And therefore, we swap false back again into ready if it is true. So the second receive will also return the panic of no message available yet when we add this adaptation there. So yeah, there's still one open issue, and it was I was thinking about before some slides. This is leaking, and it is leaking as long as there is something stored in maybe on init and not moved out, and therefore we have to implement the drop method, and here we again need the ready atomic boolean, and now with this secondary atomic boolean in use, we can be sure, okay, this is only true if a message is still there, because otherwise we would call drop on something that is not there anymore. And yeah, what is also quite interesting, if you use this assume init too early and you didn't had an initialization, so there's just random memory, you could end up with deleting some thing of the heap that points to somewhere random. I'm at the moment not 100% sure what happens when this has been moved out. If there's, so my expectation would be that there could happen something like a double free in this case. If you would if you wouldn't keep track of the ready like we did with the swap. And yeah, here's also a first test of our channel implementation. So we just create a channel and save the current thread. And then we spawn another thread that sends a message. And yeah, unpack the threads that works for receiving. And the receiving thread itself, it is in a while loop, parking itself as long as the channel is not ready for receive. And when we actually add a second send here, we get at least a panic at runtime. So we have improved a lot on safety with this runtime checks. What was quite nice, what I really liked was this idea of, okay, we just use a U8 instead of two atomic pools. We spare a byte. And I was immediately remembered on the type state pattern. Also, it is not applicable here, but yeah, what I think what is quite nice in the send message afterward, if you have like this states, and in the send message you go from empty to writing first. We are a compare exchange, and you say, okay, I have to be in empty, and I go in writing. Otherwise, I know I I try to send more than one message. And yeah. So that is before we write. We ensure we have a state change that we will write in one thread. The thread is selected. And after the write, we can release the ready state to receivers. So there we are actually quite convinced that nothing happened in between here. So we can just use store. Okay. So we now did see 4 implementations, 3 to go, and we will now use the type system to come up with a safe API. And that's something I really want to highlight here. Like I think coming up with those runtime threads and the panic, it's maybe a good first step and quite easy. I think Mara also has this message in her book that it's a good start, and then you actually want to use the type system. And well, I had the type state pattern in head, but saw something that that was a aha effect. That was this usage of several types. So we just have a generator method channel that generates also sender and receiver pair. And sender and receiver itself, they have the messages divided between each other. So here's a send message. That's quite important. It consumes self. That means after we did call this message, we cannot use the object anymore. Oh, and I got rid of my wall. Yeah, so there it is, and here. So receive has the same. And is ready, you can still call it as much as you want. Okay. And for the actual implementation via arg, which is a asynchronous reference counter or thing. So we have in the sender and receiver channel variable that is stored, that is an arg, and the channel itself, it is not public, you see here. And well, we already know this from the implementations before, and we need the traits. And then we have this generator method channel, which actually generates an arg with a new channel. So here is the previous construction. And then we clone the arg one time, adding 1 to the reference counter and move it 1 time and ending up with 2 in the reference counter. Okay. Yeah. So I did set this already. Send gets consumed, but the rest of the method it remains the same. And yeah, here in the case of receive, we still have a panic here. And what is not in the implementation now is the drop behavior. We need to add it, but I didn't do it out of laziness. But here we have some implementation. What is really changing is like, okay, we now have a sender and a receiver, and these 2 objects are of different types. Okay. And the rest remains the same. We still have we have now the compiler error. That's a great improvement. So at design time, we see, okay, we cannot send 2 times. So if you undocument it, you get a value used after move here. And a nice error message. Okay. how can we further improve? So if you like performance a lot, and you may be aware that allocation on the heap is always, can lead to performance misbehavior. So especially when cache misses are involved. And so now we use a trick that is also quite convenient. So we make channel a public type first of all, and now instead of an arg, the sender and the receiver both have a reference on the channel with a lifetime A, and this leads to another kind of generation or construction. And we use new now to ensure that the channel is uninitialized or in the like fresh state. And we have another method called split, which splits up a channel into this pair of sender and receiver with a chained lifetime. And what we actually can do here is we sure, because we have a mutable reference, that here we are the only one that holds the reference, because there's just one mutable reference. And then in this scope, we start to split it like into our two objects. And that is quite a nice trick to change interfaces and ensure safe APIs this way. And well, this interface messages, I did copy them here, but what did change was we need to take the unnamed lifetime wizard. So there's not happening too much. And also the drop implementation, it doesn't change to our previous implementations. So now we still have some problems, and I will shortly highlight them. First of all, we still panic in receive. And second, we have always in our client code the park and unpark methods. And in the next implementation, Mara proposed to just get rid of it. So we have to have some trade-offs in our design for that, but I think that's a great way to show some examples. And what changes now is we get in the sender receiving thread object. So we just memorize which thread has the receiver, and in the receiver we get a phantom data, which is a zero size type, and just ensures that we cannot send the receiver to another thread, and that is quite important. Otherwise, we could unpack the wrong thing. Now the split function changes a bit, so we need to add the phantom data here, and we use thread current, and that means like the receiver has always to remain on the same thread that called split. And then TA, so this guy is also TA, and we don't want it to change. Yeah. And then by adding one line to our sender here, we actually inform the receiving thread of that there is something to receive. And in the receive method, we have now no panic anymore, but a thread park call, which is optimal because we thought about the design and ensuring that the receiver remains on the thread it was created. And yeah, so we end up with a much shorter test function. So I think it's maybe 70 or 65% in length than before. And what is quite interesting is now the Rust compiler, because we use the phantom data to really have some design constraints on compile time. When we exchange those lines, we will end up with this error message below. And it will just say to us that here you cannot call this because it has been sent to other threads. It cannot be sent to another thread. Sorry. Yeah. So that were the 7 implementations. I also added some further readings here. One about the type state pattern that I like a lot. So it's just changing the type to have another interface if you change the state, like having a open file or having a connection established in network context. And well, this didn't ended up here. It was to I think this is quite funny because in C++, like everything can happen. And in Rust, they just decided, okay, a string is a pointer, a lang, and a capacity. And that is quite nice to reason where your data ends up. Because when you read this article, you will learn, okay, in C++, it's really an implementation detail, in which cases your string remains on the stack. And this is like a small article about how you can really get really great performance improvements by utilizing the cache well, have a low cache miss to cache hit ratio. And yeah, that is the summary on this chapter. We started with this easy implementation. We did go a bit deeper down the unsafe methods in the docs, so it's always good to read a bit more about it. Well, I talked a bit about leaking shower copies, duplicates, and the heap. I think, yeah, it's quite important topics if you feel like using Rust as a system programming language. And yeah, we use panicking to come up with a safe API. But yeah, I'm actually a fan of these APIs, and I think there are a lot in the Rust ecosystem that have a lot of checks in the compile time already and makes the life of programmers much easier and also products much more robust. So that was one of the tricks. We can consume objects and then ensure that something is only called once, for example. And we have the split of one exclusive borrow. We can make many shared borrows as we like. And that's also great help sometimes to come up with a safe API. And we actually used phantom data that was already seen in previous talks, I guess. And yeah, with this, yeah, I would close the chapters, and I'm happy to have some further discussions about what was on your mind when you read these chapters. I shared a bit of mine. So thank you very much for listening.
That was great. Thanks so much, Tim. So, does anyone have any questions?
No, I stop sharing them. Can you see this thread, the chat? Up.
We had a slight side chat about when to use a spin lock. Very, very rarely, I think was the
Never.
conclusion. never for most of us.
I ended up reading a lot about how you implement stuff like mutex, and I think they actually do spin lock really shortly for some time in
They
the
often-
implementations often, and I actually didn't came up with a good answer. What is the difference between like spin loop method and there's another one, it's called thread yield. And yeah, so I found some documentation pull requests, but yeah.
Yeah, there's often a bit of a hybrid approach, isn't there? Under the hood. I think the key bit is probably don't implement your own, and a lot of mutex types, as you say, will be doing the bit you would want a spin lock to do anyway, but doing it smarter.
Like that is really what I felt like. I think I told you in my PhD I implemented like one sender, one receiver channels, which put workload onto threads that were monitoring a secondary process over COM interface. So I did implement it a lot of this with the C++ synchronization stuff, and this outer process, it could hang like in an endless loop, it could crash, and then I had to handle like timeouts and stuff like that. And there were so many, like the first implementation was fast, but I think I needed a lot of time to actually understand where bugs came from, because they were so rare in those border cases like timeouts or something. Yeah.
My understanding of like mutexes and then also something came from the chat was read-write locks, is that they're hardware specific. So we'll hopefully get onto, I'm not sure how much that goes into the next chapter, but if it does, that would be nice. So different operating systems will decide on, particularly in read-write locks, how much it cares about starvation of the writer, because the problem with like a read-write lock is if all your readers are constantly reading and you've got one writer that's waiting, then your writer might just never get a look in. So it'd be interesting to see how different OSs manage that. I think it is OS specific. I think of anything else.
I think for me, the most interesting find in the chapter was the maybe uninitialized. I didn't know about that, so that was very interesting too. Like it's the sort of unsafe version of option. So much potential.
I still don't understand it yet, but I haven't really studied it that closely.
Yeah, me neither. I mean, I've just kind of read what's in the chapter, but
I think it's just like an option without the flag to tell you whether or not it's filled. So it's just slightly more optimized. So you never check a flag. You just treat it as if the data's there, which essentially is undefined behavior if you haven't put these other guards in place. So it's like, well, if you're putting those guards in place already to write your own lock, why would you take the hit of an extra bool essentially, or bit or byte, or however it ends up getting implemented.
But an option could double the size of a type. So if you have like an option int, for example, which is 32-bit, and I32, then the option is going to be 16 bytes. Sorry, if you got a 30-bit 4-byte integer, then the option is going to be 8 bytes. And the Rust can optimize options if it knows it's non-zero, or and in fact, it will do that with references. So an option reference will be just null underneath, and so it won't have that extra enum, the tag field, which is really useful. So if you want to have magic numbers with an option, let's say an int, and you want 0 to mean no value, you can use the non-zero int version, and it will optimize if that's what you want to do. Right?
Oh, really? I didn't know about that.
Yeah, well, there may be on it basically just gets rid of the tag completely, right? So it'll just work for things that can be zeroable, but you know the trade-off is you have to do the manual safety checks at runtime.
Yeah,
that's useful. I didn't realize that about the non-zero integers. I mean, I understood that it represents for things like, as you said, references. What you're looking for is that type has no.
Yeah, it's really cool that.
Just all 0 bits, then it can just optimize it. So that was always an issue with zeros, obviously all 0 bits. So
Does it actually do it for anything other than a ref T?
So it's basically what it's essentially doing
Anything
is
non-zero.
anything that cannot be represented by all 0 bits essentially. So that's why it does it for references, because they're meant to be sort of, as I said, non-null, so that the null being represented by all 0 bits. So that's essentially why they call it null pointer optimizations, etc. with these sort of enums. So it's just saying there's one variant that can be basically represented by 0 bits. Everything else is going to be the other variant. So it doesn't need to have the whole tag.
There's a special type in the Rust dynamic called non-zero. Is a generic type. So if you do a non-zero I32, it can never be 0. You can't assign 0 to it.
Okay, thank you. Look into that.
And so if you stick that inside an option, then it will use the number 0 meaning to none.
I see what you mean now. Got you. Yes.
So in terms of like when that optimization actually kicks in, I know it's slightly off topic. And you say any non-zero type, is that like a trait? Is that like, how does it know which type is non-zero? Or is it only built-in types?
I mean,
Michael's doing stuff there, yeah, right? Like when you do an enum with foo with A and B, it can choose a third magic value to represent none, and it will optimize that way. And that's why you got a single byte. Same with option bool. You can have 3 values for true, false, and none. The Rust compiler on option is quite cool, and so don't be frightened of using option. Now I'm not aware that you have the same optimizations in C++ with optional. I don't think you do, but
I don't think so either. But what I understand is like you don't have like initialization at all. Like you have just a random memory access at the beginning, like going release mode, C++, and just have the variable declaration. That's what happening with maybe uninit, right?
I've got a link somewhere. There's optimizations and results as well.
I'll have to read it multiple times to get it, I think, but it's interesting. I think, I don't know if this was mentioned earlier because I joined a bit late, but John King said he also did a YouTube series. I think maybe it's part of Rest of Rust on spin locks. That's a different implementation than what we have in Mara's book. So yeah, if you're interested, I think I would also check that out.
Yeah, the non-null as well for pointers and things like that. Any reference and inbox, because they're nullable, right? They're non-nullable rather.
Yeah, I was just curious if there was like an exhaustive list of like, when does this kick in? Because I never like to guess if I can avoid it in terms of when it'll be there and when it won't. Although to be honest, very rarely do I care about one tiny bit of memory in an option, but when you do, it's very good. One bit in this chapter that I was saying to Tim before this started, that I just took my brain a second to understand was just the get mute that's used in the drop methods. Because obviously, like everywhere else that we're dealing with atomics, we're dealing with ordering. And that's kind of been so ingrained in my head. It's like, of course, you must have ordering on every operation, apart from get mute, which doesn't need one. So that's it on line 100 for page 100 for anyone looking at themselves at the bottom.
I also think, like, especially like in the special case of drop, you can really be sure that there's just one thread dropping at the moment because there's just one mutable outer reference, right?
Yeah, that makes sense to me. There's one owner, right? So therefore, the owner is on a single thread.
Mm-hmm. But what happens, because I think it is in the documentation, I have to double check now, it is a safe message. So what, yeah, you could end up.
Well,
I mean, both the sender and the receiver have the message, and they're not necessarily dropped when the channel's dropped. They could be dropped. Oh no, sorry, they are. They are necessarily dropped, otherwise the channel can get dropped. Wait, is that true? Yes, they must be dropped, not if the channel be dropped. Yeah. Yeah, but it
when I understand this correctly, there's also the get message, right? And it also returns a mutee, but it's a pointer. So that did get me really confused when we were talking before the presentation. Like,
I watched the first video of Herb Sutter's explanation of memory ordering, and in my opinion, it explains it a lot better than this book does. Because Herb's uses more visual diagrams to explain where the fences are and the barriers and how ordering works. Uses
is that the link you shared on Discord?
Yeah,
that's one.
Yeah, someone shared it in the during the last meetup, I think, and so I added it to the video links. I think it's important to remember that the Rust memory model is based on C++ memory model, and also Herb has a lot, famously incredible speaker, incredible at explaining stuff. I think as well, like this book is it goes quite a long way beyond memory ordering. I think if this was an entire book on memory ordering kind of thing, then it would probably go into a bit more detail and kind of have a few more diagrams, but it's definitely, it does assume things slightly differently probably than the video does, because that was like the first introduction to this stuff getting introduced. There was nothing really like it at the time, as far as I'm aware. That's the first formalization of memory ordering.
It shows where the advantage of slides over books in this particular case. But I just thought I'd mention it because when I did go watch it, it's like, okay, now remember, because you got to remember that memory ordering is nothing to do with multi-threaded. It's just purely to do with making sure certain statements and expressions are put after certain other statements and expressions. And so when you acquire, you're saying that everything that's happened before, I now expose that to you, right? And that everything that happened before is guaranteed to have happened. So at that point, any other thread is looking at the same variable that you've just acquired, you know that any associated value before it has changed, and the release is the opposite. And the Herbstadter thing really does show, so kind of like show diagrams. Well, it basically shows arrows and shows what, shows examples of ordering and so forth, and what would happen if you do the wrong ordering.
So I've spent the last 2-3 weeks rereading that chapter on memory ordering. It still does my head in. I think the only time I actually understood anything was when I started to think about it in terms of compile optimizations, which are reordering.
Yeah, and see, but it's more than that.
Doing its own thing in terms of deciding which instructions to execute. And also, when I also started thinking about caching and cache coherency, in terms of when the CPU decides to cache, so when it uses cached writes or cached reads per thread, and so when it actually decides to start synchronizing those caches of its writes, or its reads, and when it's actually, starts to store things in main memory. So that was the only time I actually understood what it means by these happen before relationships.
So the CPU can do some reordering as well. For example, if you're reading from memory to a register and then writing out that register to another memory, obviously the write is dependent on the read, and so while the CPU is pipelining those instructions, it can do unrelated instructions at the same time, maybe adding 2 other registers which have nothing to do with the register you're reading to and writing from, right? And so it could put that in between the read and the write if it wanted to, right? You don't know what the CPU is doing. You're just guaranteed that it will retain the illusion that things are happening in sequence. And the acquire release stuff protects you against that. And so what I'm saying is that the instruction reordering isn't just compiler, it's also CPU on the silicon, and you don't see that.
I think the bit that got me is the bit that you said, John, there about cache coherence and the idea that like one thread's view of the same memory can be different to another thread's view of the same memory at the same time. Correct. And that's the bit like, once you realize that, then you're like, okay, well, how do I even reason about this at all? And then that's where this idea of memory ordering comes into, where suddenly you're like, okay, there are certain guarantees I need to make at different points. I need to make sure that the CPU knows that I need to have these threads, in sync at this point. I need these ones to be aware of these changes. I need these ones to be aware of those changes. And I think when I first, initially when I first read about atomics, I was thinking of it as a single atomic, and that's all there ever is. And when that's the case, memory ordering doesn't matter, because as Mara kind of restates in the book, any individual atomic will have will change in a predictable order. Like everyone will view the values of that atomic in the same order. What they might not view is the values of the other data in the same order relative to that atomic ordering. And then that's where you build up then, okay, well, now we need acquire release, or in very extreme cases, you might want totally sequentially consistent. So it's,
yes, you only care about memory ordering if you've got associated data to the atomic. If you just have the atomic, you don't care about memory ordering. And on the Intel processor, you've got compare and exchange CAS, called CAS instruction, which will do the syncing across L1, L2, L3 caches and so forth for you. And it does the, I expect this result, and if it have this value, then I'll write this value, and that's the one instruction on the Intel processor. I'm not sure what the ARM processor is. I guess it's something very similar, and pretty much everything related to atomics uses that single instruction. Yes, as Gareth said, the memory ordering, you only have to worry about that if you're saying, okay, I want to set this local variable in this function, and afterwards I want to set this atomic, notifying anyone else that cares that this variable I set before has changed. And you don't want the CPU or the compiler moving that, changing the variable after you said, okay, this atomic now is set to true because I've changed this other value. and you want to ensure that that change of that other value, which isn't protected, happens always before the atomic write. And so when another thread looks at that atomic and says, okay, now I know that this is right, that's a guaranteed, right? It's consistent. And Herb Sutter does go into detail about it, a lot more detail than the book. And that kind of helped me try to grok it. It is a mind-bending subject for sure.
So where's the link for this person you're talking about? Just so I can
Are you on Discord at all?
Oh, no, I wasn't on Discord. I was just on this chat.
Okay. I'll see if I can dig it out for you.
It's linked from the
So it
memory
is-
ordering video on so
I
we
just-
post the recordings of those
found it.
meetups. You got it? Okay.
Yeah.
Yeah, I just posted a link.
Okay, great.
Yeah.
Someone just beat me to it.
Thank you.
You did, yes.
My author.
Because
All that
I
effort
was
for nothing.
sorry.